Welcome to this session. This session will give the third problem on how to solve initial value problems given some differential equation with some initial conditions by matrix method. So the first step is to know that these initial conditions given, we can write them as y of 0, y at 0, y prime at 0, and then y at 0 is 1, y prime at 0 is 0. So this will help us now to find the values of the unknowns C1 and C2 after getting the general solution, and then the solution to this differential equation will be the value of the function in the first row. For the first row is what defines the value of the function, second row is the derivative of the function. So step one is to write the matrix, write the equation given or the differential equation in system of two linear differential equations. So you start by saying, let y be y1 and dy1 dx is actually the same as dy dx be the same as another variable y2, call it equation 1. And then d squared y dx squared, according to the equation, is given by minus 4y. But this is the same thing as saying d squared y1 dx squared is the same as minus 4y1, because we've said that let y to be y1. And then to get d squared y1 dx squared is the same as d dx of dy1 dx, and dy1 dx is y2, so the same as dy2 dx which is the same as minus 4y1. So call this one equation 2. So from 1 and 2, we have a system of two linear differential equations of first order. So we have dy1 dx equals to, we can write 0 y1 plus y2, and then this other one we can write dy2 dx equals to negative 4y1, and then plus 0 y2. Now from this, we write the matrix system as dy1 dx, dy2 dx equals 0, 1, minus 4, 0, and then y1, y2. So it's like we have the system y dot is equals to a times y, where y is this matrix here, and this is the A matrix. So the next, we get now the eigenvalues of A, and eigenvalues of A are obtained by solving the equation determinant of A minus lambda I equals to 0, which implies determinant of, so this will be 0 minus lambda, 1 minus 4, 0 minus lambda should give us 0. So this will be determinant of minus lambda, 1 minus 4 minus lambda equals to 0. And this is the same as lambda squared. Minus 1 times minus 4, this is 1 times minus 4 is plus 4 equals to 0. So lambda equals to plus or minus 2i equals to now square root of minus 4. So eigenvectors is the next step. So for the complex eigenvalues, it's easy to find eigenvectors because just picking one of the eigenvalue will result into the two eigenvectors. So let me pick the positive eigenvalue, which is 2i. So because we are dealing with a 2 by 2 matrix, then eigenvector will be of the form x1, x2. Now we need to solve this equation. A u equals to lambda u. This is the equation that will help us to find the value of the eigenvector u. So the A matrix is 0, 1, minus 4, 0. U vector is x1, x2 equals to 2i, which is the lambda, and then times u, which is x1, x2. Now 0 by x1 is 0, 1 times x2 is x2, minus 4 times x1 is minus 4x1, plus 0 times x2 remains minus 4x1 equals to 2x1i, 2x2i, from which this is the same thing as saying x2 equals to 2x1i and minus 4x1 equals to 2x2i. Call this equation 1, call this equation 2. We should be able to see that equation 1 and equation 2 define the same thing, are similarly the same equation. So if we let x1 to be t, where t is any non-zero real number, then x2 will be 2ti. So it tells us that our eigenvector u given by x1, x2 will be, where there's x1 we put t, where there's x2 we put 2ti. You can factor out t, so we have 1, 2i, and then times t. Remember, t is any non-zero real number. Now, letting t to be 1, then u will be 1, 2i. But this can be written as 1, 0, then plus 0, 2i. What is making me to split into two is to ensure that I have the real part and the imaginary part of the vector. So u will be 1, 0, plus factor out I into 0, 2. And so we call this real part, we call it B vector, and we call this other part W vector. So you see one eigenvalue, 2i, has helped us to get two values of the eigenvector, V and W. So that's why it's very easy to deal with case of complex for 2 by 2 vertices. Now, we know that solution x of t, y of t, is given by y of t is e raised power lambda t times vector u, which will be e raised power lambda is 2t, 2i, so it'll be 2i times t, so it is 2 ti. And then since lambda is 2, that's what has resulted into this vector. And then u, which is given by 1, 0 plus I 0, 2. Or for convenience, you can just write V plus IW. So 1, 0. So using Euler's identity, e raised power theta I is cosine of theta plus I sine theta. Then we have y of t is cosine of 2t. Now remember, so for this given differential equation is not, there are none, or the independent variable is x, so it's just better to use x was given the equation. So the independent variable for this case is x not t. So this is x. So we'll have, so this y of x, not y of t. If the independent variable is given in terms of t, then use t. So this is x, this is x. So x, so xi. So will be given by cos of 2x plus I sine of 2x. And then multiplied by these vectors, 1, 0 plus I 0, 2. Now, after doing this, let's do multiplication. So y of t, y of x. So I'll have cos of x, 2x times this. So cos 2x times 1, 0. And then plus I cos 2x times 0, 2 plus I sine 2x 1, 0. I times I is minus 1, so minus sine 2x 0, 2. Now collect, okay, before collecting the real parts and the imaginary parts, let's just simplify this. All this be cosine of 2x 0 plus I 0, 2 cosine of 2x plus I sine of 2x 0, and then plus 0, and then this minus 2 sine 2x. Now we bring real parts together and imaginary parts together. So this one and this one are the real parts. This one and this one are the imaginary parts. So we'll have y of x is given by cosine of 2x 0 plus 0 plus minus 2 sine 2x plus I 0 plus sine of 2x, and then 2 cos of 2x plus 0. That will give us y of x is given by cosine of 2x minus 2 sine 2x plus sine of 2x twice cosine of 2x. There's an I. I remember from what we discussed in the introduction, for the case of complex, this is what we call x1 of x. This is what we call x2 of x. Then by superposition principle, okay, because now the variable here is y, then we call this one y1 and y2 not x. This x, then we call it x. Y, let's not interfere with the notation. So y1 of x, y2 of x. So by superposition principle, the general solution is y of x equals to c1 y1 of x plus c2 y2 of x, i.e. y of x will be c1 cosine of 2x minus 2 sine 2x plus c2. Now there's no I, so what matters just this imaginary part of the complex unit. Sine 2x, 2 cos of 2x. So this is our general solution. Now, we were given that from this same problem, we were told when y of 0 is 1 and y prime of 0 is 0. So we use this condition to find the values of C1 and C2. So remember I said this can be written as capital Y of 0 is 1, 0. And this notation shows that the first row is the function, the second row is the value of the derivative. So y, capital Y of 0 equals to C1. So where there's x, you put 0. So cosine of 2 times 0 minus 2 sine of 2 times 0 plus C2 sine of 2 by 0, 2 cosine of 2 by 0. This should give us, according to the initial conditions, 1, 0. Now, cosine, this 2 times 0 is 0, so cosine of 0 is 1. 2 times 0 is 0, sine of 0 is 0 times minus 2 is 0. Two times 0 is 0, sine of 0 is 0. 2 times 0 is 0, cosine of 0 is 1. 1 times 2 is 2, equals to 1, 0. Now just multiply by these colors. So we'll have C1 plus 0 C2 and then 0 C1 plus 2 C2 gives us 1, 0, which tells us that, which implies C1 equals to 1. And from this second equation, 2C2 equals to 0, which implies C2 is 0. So hence, therefore, the solution is capital Y of t. So C1 is 1. And then so 1, and then this one because 2x plus 2x, and then minus 2 sine 2x. This other part for C2 we don't write because C2 is 0. So 0 times that vector is just 0. So hence the solution to the given initial value problem is y of x. Remember the value to take the first row, cosine of 2x. These are the row just the derivative of the previous, the derivative of the value of the function. So this is the solution to the given problem. Thank you.